Okay, so as I say, welcome. My name is Liz Woodham and I'm one of the members of the NRICH team. We're based in Cambridge, and I'm joined this afternoon by Claire Metcalfe and Ems Lord. And the three of us will be leading the session this afternoon. If you've attended one of these before, as I said earlier, you may know that we're really grateful to Trinity College here in Cambridge because they fund these webinars so that you can attend free of charge. So we do want to point that out and say thank you very much to Trinity College. During this afternoon, we're going to be working on some maths together, and at various points we might encourage you to contribute your thoughts to the mathematics using the chat facility. So please do that. And if you would like to change the way that your name displays, then please do click the three dots on the edge of your window so that we can refer to you clearly. The idea of this afternoon is to introduce you to some of the latest problems in the secondary and post-16 features. I'm not going to say any more about them at this point, but instead I'm going to hand over to Claire, who I think is going to take us into our first task. Thank you, Claire.
Yeah, so I've got a problem for you to think about, Liz, which hopefully is now being displayed.
Yes, I can see some circles joined up.
Yep. So I've got 6 circles and they're joined up by arcs. And I want you to think about, so I just need to find the annotate button. I want you to think about the numbers 1, 2, 3, 4, 5, and 6. Yep. And we're also going to think about something called positive differences. So I believe there used to be a symbol for this once upon a time. So the positive difference is the where you take the biggest number, subtract the smallest number. So if we take, so I think the symbol was a tilde.
Oh,
so 2 tilde, let's have 5.
Yeah.
The positive difference between 2 and 5, which is 3.
3. I understand. Got you. Yeah.
And what your task is to try and place these numbers into these circles so that when 2 numbers are joined together by these arcs, this number here is the positive difference. So if I had 2 and 5 in here, then the positive difference between 2 and 5 is 3. So that would have to be a 3.
I see. Okay. All right. Yeah.
I'll get rid of some of this stuff in here and let me know what your thoughts are on how to approach this.
So I guess when I'm faced with problems like this, sometimes I find it's quite helpful to start at an extreme. I don't know whether that might work today. So I'm going to go, let's think about the 6. I'm going to try something out, Claire, and see what happens. Okay. So I'm going to pop 6 in the very top of your image.
Okay, so we're going to have 6 right at the top.
So what you're saying is that 6, therefore, has to be the positive difference between the 2 numbers below it.
Yeah, these 2 that I've just put dots in.
Ah, okay. So I can see straight away that's not going to be possible because I've chosen the largest number to go at the top there, and all the 5 numbers we've got to choose from are smaller. So I'm never going to get a difference of 6. So although I guess students might think that is disappointing, actually I've learned something. So I'm quite pleased that doesn't work.
I think I agree with that reasoning.
Yeah. Okay.
I'll get rid of that.
So perhaps if I was going to be quite systematic about this, perhaps I'd then think about the row below. What would happen if I put a 6 in one of those circles below? Well, you see, straight away, I'm thinking that was actually, I should have thought a bit more because I'm still not going to get a difference of 6, am I? So I reckon, Claire, that 6 has got to go in the bottom.
Okay, so we think 6 has to, well, we've just deduced that 6 has to go in the bottom.
Yeah, okay. I can
somebody's asked a very sensible question, which I should have said. It's using each number once and once only.
Yeah.
So each of those 6 numbers has to appear once only.
Yeah, okay.
So I think it's probably a good point now to ask people in the chat, can you deduce anything else about where numbers can go and can't go? So Liz has deduced that 6 has to go in the bottom row. Can we work out something about one of the other numbers? So, okay, we've got 5 as well as a suggestion. Does that mean that 5 can't go in the top and can't go in the middle row? Well, let's have a think about that. So we've got somebody who says 5 can't go in the top, but it can go in the middle. 5 can go in the middle. So for those of you who are saying that 5 can't go in the top, why can 5 not go in the top? Now, that's a lovely bit of reasoning. So if 5 is in the top, the only way you can make 5 as a difference is between 1 and 6. And we've already deduced that 6 can't be in the middle row. So 5 can't be in the top. But we don't know. It could be in the middle row. We don't know. And it could be in the bottom row. Is there anything that we can... 3 can't be in the bottom row next to 6. Okay, Jackie, why can 3 not be in the bottom row next to 6? Or anyone else? Because we have a difference of 3. So we can't have a 6 here and a 3 here, because then we'd have to have a 3 there. Here's another question. Can we have 5, 6, and can we have 4, 5, and 6 all in the bottom row? No, because you can only use once. Okay, so I can't have 4, 5, 6 in that order or in the reverse order, but could I have 4, 6, 5? Is that possible? Okay, so if we followed that logic, the difference here would be 2, and then we'd have a 1, which then would mean we have to have another 1 there. So we've just thinking about a few numbers, we can deduce lots about this problem and really reduce the number of possibilities to quite a small number. So this is the first problem we're going to talk about today, and I'm just going to clear my drawings and find the NRICH website. So if you're not, oops, I'm still on annotate, which means I can't use my mouse. If you're not sure where to find the current feature, then probably the easiest way to do this is go to the secondary teachers button up here, or you can click on this nice picture of balloons there. And when you go into that, you'll have a button for the latest feature. So in this, we have all of the Key Stage 3, Key Stage 4, and Key Stage 5 problems. Students, if they go to the post-16 or the secondary students, if they go to secondary students, they'll get 11 to 16 problems, and post-16, they'll get all the 16 to 18 problems. And sometimes there's an overlap as well. But if you go to the teacher one, you get all the problems across the 3 key stages. And the one that we've just been looking at is called positive differences. I'm just going to make that a bit bigger because it's a little bit small. So you'll see here, this is the same problem we've just looked at, and there are a few hints for students to think about, sort of similar to how we've been doing it. There's also some more hints in getting started. So that includes the can 4, 5, and 6 all be in the bottom row. So there's lots of things there for students to get started on and try and reduce the actual numbers. And if I remember rightly, there's only 2 possible ways of doing this. That's the first problem that we've featured in this half term. The next one I want to think about is something called 11 by 11 square. And this one's similar, but slightly different. So I'll just talk through what the problem is. So we're talking about an 11 by 11 square. That means a square which is 11 long and 11 up. And I've probably just drawn that where my video is, which is very non-helpful. So these squares are 11 by 11. And we've got 5 rectangles, which are going to have different widths and lengths using each of the numbers 1 to 10. So like in the previous ones, each of those numbers has to be used once and once only. And this problem is a bit harder. So to help us along, there are 3 pictures there. Only one of those pictures is possible. So Liz, looking at those 3 pictures, can you work out why one of them is definitely not possible?
Okay. All right. So if I look at the left-hand image, Claire, the one on the very left, I can see that the bright green rectangle and the pinkish rectangle, they have both got the same height. So I think that according to your rules, that's not allowed, because we've got to have when I say height, I guess I mean length perhaps. Anyway, the longest dimension is the same on both of those rectangles as drawn, which isn't allowed.
Yep. There's actually another reason why this picture isn't possible. I wonder if anybody in the chat can try and find another reason why this picture is definitely not possible. So remembering that the dimensions have to be 1 to 10, and we're trying to make an 11 by 11 square.
Yeah, I think Susan's noticed.
Yeah. So this one's got an 11 at the bottom. So that's no good. So we know that one's, I'll do a big cross in that one. That one's not possible.
Yeah.
Looking at the other 2 pictures, can anyone suggest why one of those is not possible? Okay, so we've got a couple of people suggesting that this one is not possible. Can anyone identify by colour 2 rectangles which are breaking the rules, if you like? Okay, so it's got pink and green because they've got the same width or a shared dimension. Is there another pair that cause a problem? And I apologise for people for whom trying to distinguish between these colours is quite difficult. Yeah, purple and blue. So they've got a dimension in common as well. So we know that one can't be, that one's not a possible arrangement. But this one seems to be okay. So what I'm going to do now is I'm going to ask Liz to share something she has prepared earlier in the best Blue Peter fashion. I'm going to stop sharing.
There we go. I'm hoping you can see a very rough sketch of that arrangement that we've decided it could be possible.
Okay, so how can we proceed by using this? Is there anything that we can deduce? Might be helpful to write the numbers 1 to 10 at the top so that
That's
we can.
Good idea, Claire. Yep, I'll do that. Okay. Just try not to knock my. So if I write the numbers 1 to 10, 1 is that? Yeah, that's for 2, 3, 4, 5, 6. Okay.
Okay. What do we know? Is there anything we know about the dimensions of the rectangles, which are, oh, somebody suggested something already, which is brilliant. Someone suggested 1 and 10 on the base.
Yeah, should we try? See what happens? Yep. Okay. So if I'll pop a little 1 here.
Yeah.
10 here. Okay.
Okay, so we've got a 1 and a 10 on the base, and that means that those add up to 11. So is anything, can anyone suggest any possibilities for the dimensions of the rectangles along the other sides? So what could the top 2 dimensions be? So in the chat, what could those 2, what are the possibilities there? Okay, so 7 and 4. 4 and 7, I'll count that as the same.
Yeah.
This is why I'm trying to resist the urge to try and write on your screen, because I can't do that.
Would you let me know, Claire, when you would like me to write? I'm holding off just for a while, but do let me know. Okay, 3 and 8. Yeah.
Yep. Two and 9. So it might be helpful to just write pairs down the side. 1,
Yeah,
10.
that is a good idea, isn't it? Okay, so I'll pop those over this side of the paper.
Yeah.
So we've got pairs to 10. So would you like me to include the 1 to 10, Claire?
Yeah, let's include that.
Yeah, okay. I'll try and be relatively systematic so that we've so I don't miss any out.
We've had 2 and 9. We've had 3 and 8 suggested as well.
We had 4 and 7. Nobody suggested 5 and 6, interestingly. I wonder why not. Is the rectangle drawn to scale? That's a really good question, Susie. No.
No. What
that
we've
would
done,
be giving too much away.
What we've done is we know more or less how the rectangles must look. And now we're trying to work out if we can knock out some options.
Yeah.
So we've got 5 pairs of numbers which sum to 11.
Yes.
We know that 4 of those pairs have got to go on the outside.
Yes, they do, don't they?
So the missing pair of numbers must be the dimensions of that middle rectangle. So we can maybe knock out some of the options. So would it be possible for that middle rectangle to have the dimensions 2 and 9?
So if this was 2 and this was 9, okay, would that be possible? Pop your thoughts in the chat.
And then the next question is, why not?
Yeah.
Which is a bit harder to type in.
It's harder in the chat, isn't it?
Yeah, so if that middle rectangle had a length of 9,
yeah,
and we've already got a 1 out that side,
so this
then
whole thing,
so that whole line is 10,
but
so that
would not possible.
Yeah,
given the edge
we'd have to have a 1 on the other side as well, which we haven't got. So we know that 2, 9 has to be a pair of edges. So we can, we could write E next to that if you want, or edge.
Yeah.
And similarly for 1 and 10, we know those have to be the edges.
Oh, how do we know that, Claire?
Oh, how do we know that? Well, if 10 was going to be in the middle, then we'd have to have those other 2 rectangles either side adding up to 1. Which I don't think is possible if we're going to stick to integers anyway.
No, nice. Okay.
So we're not going to run through the whole solution here, but by sort of starting with this, you can start to maybe reduce some of the possibilities. And I'm trying to remember what order I did things when I was doing this. I think probably I probably started looking at the top line.
Okay.
So if we
have a little go.
Yeah, let's have a go. Let's say that 2 and 9. So we'll say 1 and 10 at the bottom.
Yeah.
And let's say 2 and 9. So with the 2
up here.
Yeah. Yeah. So the big one being 9. Okay. If that's going to be my rectangle, then I think the rectangle in the middle has got to have a width of 8.
Yes.
From what we've done before with the pairs, that means that middle rectangle has got to have dimensions 8 and 3. Because that was 1 pair.
Yes.
So that means that my other 2 sides have got to be 4 and 7 and 5 and 6.
Yes.
And I've just got to move the chat because you've just written that underneath where my chat button was. Okay, so let's try one way round. So let's try putting 4 and 7, and I might ask you to delete things in a second. But let's try 4 and 7 down the left-hand side.
On the left-hand side, yeah. So 4
so
and
4
7.
there, yeah. And then that means we've got to have 5 and 6 on the other side.
Yeah.
So I think 6 is going to have be the big one. Okay, and then I think I now have a problem because I think that then implies that my middle rectangle has got a height of 2. So that's a contradiction. So therefore, I know that 9 and 2 is not possible for that top row.
Nice. And so I guess this task is it's about eliminating possibilities, exactly the same way as we did with our positive differences task that we started with, Claire.
Yep.
And this requires quite a systematic approach, doesn't it? Yeah. And of course, there are different ways to work systematically. You've chosen to, as you say, to think about that top edge. But we could have thought about the middle rectangle like we did previously. Yeah. Okay. Would you like to do any more of that one here, or shall we leave that?
I think we'll leave that as an exercise to the listener.
For others.
And we'll move back to the feature. So I am going to move chat again, which I've just put it still in the wrong place. Okay, so if we just head back towards the feature, there are another couple of questions which have the same sort of idea with the logical trying to reduce possibilities. And there's one which is aimed at Key Stage 4 and Key Stage 5, which is one about a bike race. I'll just show it, won't talk about it. But there's a bike race, and we've got 5 riders who gain points on the stages, and you know some information, and you can use that to eliminate other possibilities. And it's a case of being very, very careful with what you write down. So that's another very, very similar problem. Okay, we'll go to something slightly different for this one. This one's called Isosceles 7, and it's about an isosceles triangle. So what we have, if I just get my annotation button, and this is something I would do if I was doing this in a lesson. We've got a big isosceles triangle, and then we've got some little isosceles triangles in it. And we're told here which the equal lengths are. So I'd probably start by drawing these on. So we know that all of those are equal in length. Now, this question looks a little bit scary as it is, because there's lots of angles in there. So we have actually put in getting started a slightly easier question, which just has fewer triangles. So this is our simpler case. So if I just stick those lines back on. And there's also a suggestion here that we can call angle BACX. So if we call BACX, in the chat, are there any other angles that you can tell us something about? Okay, we've got some suggestions of some that we can work out. So we've had a suggestion that we can say that BCA is also X, because these are isosceles triangles. And then we can work out this angle to be, and this is where my handwriting is going to have problems, is 180 minus 2x. And then somebody's given me the next stage, which is this one, which is 2x. I should have made this bigger. Okay, has anyone give me another angle yet? There we go, here's another one. So that's this angle, that's 2x. Yep, shall we just keep going and let's finish it, because we're almost there. So what's this angle here? Okay, 180 minus 4x. So then we can work out this angle. Well, I'm not sure that one is 4x. You need to remember this angle here as well. Yeah, I did exactly the same thing when I did this first of all. I kept thinking, okay, it's exterior angle of a triangle, and then I got it wrong.
We'd much prefer you to participate and make the odd little mistake than
Oh, yeah.
not participate and being worried about offering perfect answers. So yeah, please don't worry.
Okay, so has I think anyone's given me this angle yet? We've got DCE, which is this one I've just written in. Can anyone give me DEC? We've got DCE. What's DEC? Yeah, 3x. So then we can work out this one, which I think is 180 minus 6x. Apologies. Okay, so what's this one? I might have to draw a bigger triangle in a second. Okay, yep, so this one is 4x. And then this means that this one is also 4x. So we have worked out that this is x and this is 4x. And this is an isosceles triangle. So this is 4x. So the final point is, what is the angle at A? So what is x? Yep, I agree with that. So x plus 4x is 9x. So we get 9x is 180 degrees. And so x is 20 degrees. So we get a nice answer. And if you have a look at the isosceles 7, the original problem, you also get a nice answer. But that's not always the case. So if we go back to the original problem, after isosceles 7, we've got an extension problem, which is for which of these triangles do you get a nice answer? And for which of these triangles do you not get a nice answer? So you can start off with just one isosceles triangle. Then you can go to one made out of 2 isosceles triangles. You'll have to excuse my extremely bad drawing. And continue like that. And you should find a pattern. And you should be able to tell which ones will give you nice answers and which ones will not. And we'll leave that as a task for to look at later.
Claire, if you were doing that, if you were in the classroom with students, then having got to that point when you're coming there to the extension task, that generalization, would you encourage them to be working in pairs to kind of try out? You were very systematic then. You had just tried your 1 triangle and then your triangle split into 2 triangles. Is that something you'd be expecting students to do?
It's the sort of thing I probably ask the students to think about it first and think about can they find any of the nice numbers?
Yeah.
And then I would say with them, okay, well, what's the simplest case that anyone's got? Okay, can anyone think about the case after that? It's possibly quite nice to go back to this. Oops, I'm on mouse again. It's probably nice to go back to this picture at the top here and think about how that's split up. So
nice.
And when I'm talking to 6th formers as well, and they have to give examples, I'm also saying, well, is that the simplest example you can think of?
Yeah.
You know, can you think of anything which is more basic? Because I think that tells you a lot about what's going on.
That's a really useful skill, isn't it, to have up your sleeve for finding the simplest case. Yeah, nice. Thanks, Claire.
Now, this problem uses a lot of isosceles triangles, and I'm going slightly off piste here, so apologies to Liz for going against our plan. There's another problem in the feature called Iffy Triangles. So we've done an awful lot in that last problem about using, if an isosceles triangle has got 2 equal sides, it's got 2 equal angles. But that's something that people sort of meet, but never actually think about, how would I prove that? So we have a problem called Iffy Triangles, which has got 4 triangle facts. And it's asking students, can you prove this? So can you prove that, in this case, if we've got a triangle where PQ is equal to QR, can you prove that that means that these 2 angles must be the same? And conversely with this one, if we have a triangle KLM, M, and you know that these angles are the same, can you prove that these two lengths are the same? So getting students to think about actually, can we prove this? We've been told it's true, we've seen it's true. Is there a way that we can actually show that it's true? And can we actually show that it works both ways? This is something that is called Euclid's bridge of donkeys. So in Euclid's Elements, this is the first proof that was considered quite tricky. But that's only because Euclid didn't prove all of the congruent triangle facts first. If you know all the congruent triangle facts, it's not too bad. Otherwise, it's a little bit trickier. Right, ooh, I'm still on annotate. Okay, I think there's probably one more problem really that we wanted to talk about today, which leads into a lot of these other problems, and that's Iffy Logic. So I've kind of hinted a bit about this already with Iffy Triangles. But this is about those symbols if and only if. So in this question here, we've got 16 statements. We've got some connections. We've got some if and only if connections. And the problem is, can you rearrange the cards to make all of these statements true? So if I just show you, we can move some about. Oops, and now I've just moved this. It now wants me to submit, but I won't do that yet. So Liz, is there anything you can notice about these statements? Or any starting points that'd be good?
Yeah, starting point. There are a couple of things that I would notice, I think, Claire. Firstly, we've got two statements about rover. They leap out at me as going together. So okay. I'd want to focus on those. So let's have a look at that. Rover is a dog. Rover is not a cat. So what we're thinking about here, so if Rover is not a cat, I can't be sure that Rover is a dog. So, but I think the other way around is true. So I think we'd want Rover is a dog. Yeah, and that's it. Yeah.
Okay, so we think that if Rover is a dog, then we know that he is not a cat.
Exactly.
Or she. It could
or
be
she. Good point. Yeah. Yeah. Good point, Claire.
I've assumed that Rover is a male animal, but might not be.
I think from there, it's interesting, isn't it? I guess perhaps we should ask other people.
Well, before we start looking at the rest of them, what students can do is they can submit part of the way through.
Oh, yeah.
So you can actually check that first statement. There's something a bit complicated with this one, though, because it is possible to get 7 correct statements, but the last one not being correct. But if students want to check part of the way through, they can do that. So if I'll just demonstrate, if I get this the wrong way around, hopefully it should tell me it's wrong. Yeah.
That's good.
So you might want to do that. You might not want to tell them about that to stop them trying to guess. Okay, so I think we sorted out Rover.
Yeah.
What would you do next?
Yeah, if it was up to me then, what I would probably do, Claire, is I'd probably do something that actually, without thinking about the mathematics yet, but I'd think about the statements which have got N and M. And those which are just N, because I'm sort of thinking that actually that could be a useful way of narrowing things down a bit.
So if I extract all the statements which just have N and M, and there are 6 of them, which is
that's encouraging that there's an even number. Yeah. Okay.
So in the chat, out of the statements we've got left to sort, is there any other grouping that you could use? So all the statements left just involve N, but is there another way that we can narrow down what we might be looking at? So I'd say there were 4 statements which are very similar, and 4 statements which are slightly different. Okay, so we've got a couple of people who've said odds and evens. So if you know, looking at this, there are 4 statements which involve odd numbers and even numbers. So what I'll try and do is I'll try and remove the other 4 statements. So now we've just got left 4 statements involving odd and even numbers. Is there any way that we could pair those up using either if or if and only if? So that could be a dash and an arrow could be going this way, and you could have a dash and 2 arrows if you're trying to type it in the chat. So is there any way we can match up any of those? Or is there any pair that couldn't possibly go together? Okay, so we've got a suggestion that n plus 1 is odd if and only if n is even. So n plus 1 odd if and only if n is even. We've also had a suggestion that n squared is odd if and only if n is odd. Okay. Liz, do you agree with those two?
Well, no, I don't think I do, Claire.
Mm-hmm.
Oh no, hang on a second. I think my initial thought was when I first would think about it, I thought, yeah, I definitely agree with the n plus 1 odd n even statement, because I'm thinking that if it doesn't matter which way round that is. If I given one, I know the other.
Mm-hmm.
N squared odd, okay, and n odd, right? How might if I was a student, I wonder what I might do. Would I try a few examples perhaps out in my head just to have a think? If n squared is odd, then n cannot possibly be even. I know that. What I'm wondering is can I approach the logic from the other way around? Yeah, I think I can. N is odd. I know that n squared is odd. I'm changing my mind. I do agree.
Okay, and you could, if you like, try and justify it by writing an odd number as 2. I can't use an n. 2k plus 1.
Plus 1, yeah.
All squared, and if you've met expanding brackets, you can show that that is also odd.
Yes.
And then to try and do it the other way, you could look at a contradiction. Is it possible to get a square of an odd number which is even? Right. It turns out it's not.
And it's not, yeah.
So let's put those 2 in, and I think it makes sense to have n is odd on this side, but I don't think it matters.
Why did you say that, Claire?
I also think the left-hand side ought to be the simpler one. Okay. So I probably would have swapped those 2 around as well.
Okay,
that's just a style. Is
that your personal preference, or is that a convention?
I think it's more of a personal preference, but I'm used to the left-hand side being simpler to the right-hand side. Okay, we've had a suggestion about n and m. So we've had a suggestion that we can link. Let me just write them down. N greater than m, and n minus m is greater than 0. So the question is, can we link that with an if and only if? Or does that only work in one direction? So what do we think in the chat? Is this one that we can do with an if and only if? Or is this one that will only work in one direction? We've got 2 different answers almost immediately. Okay, so I think if I start with the first one, n bigger than m, I think I can subtract m from both sides of my inequality, which I can do without changing the truth of the inequality. M could be negative, but then subtracting m would be like adding a number. So if you're adding or subtracting the same thing to both sides, your inequality doesn't swap around. It's only multiplying and dividing that you have to be a bit careful on. So perhaps we ought to make a new version of this where we've got n times m is greater than 0. And I think that actually you can reverse these steps and it still works. So I think I'm going to stick that one in as an if and only if. Okay, Liz, anything that you'd like to try next?
Oh, let me see.
That's a good idea.
Good strategy, Susie.
Susie, yeah,
strategy
definitely.
To think of a counterexample. Yeah. I wonder, what about this n plus m is odd? What could we do with that, I wonder?
I think this is one where a counterexample might be quite useful. So n plus m is odd.
So yeah, if n plus m is odd, we've got an odd number added to an even number.
Yep.
So yeah, they can't. Okay. So they can't be the same. Well, yeah. If they cannot be the same number, then n take away m is not 0.
Okay.
Does that make sense, I wonder?
Yeah, I think that makes sense. So m plus n is odd, we think implies that n minus m is not equal to 0. Yeah. Can we go the other way? Can we find two numbers n and m, or can we prove that you can't go the other way?
I think, yeah, I think this is where our counterexamples come in, exactly as you said, Claire. Yeah, I wonder what you think. Do post in the chat. Could we say the other way around?
Or can you find a pair of numbers n and m so that n minus m isn't 0, but if you add them, you get an even number.
You get an even number.
Okay, so somebody suggested 4 minus 2 is not 0. I'll agree that 4 minus 2 is not 0. Does that complete the counterexample? So 4 minus 2 is not 0. But there's one more step that we need to do to finish off our counterexample. Brilliant, yes. So 4 plus 2 is even. So we can deduce from that n minus m is not equal to 0 does not imply that m plus n is odd, because we've got a counterexample. We've got somebody who's also shown that if you've got a difference of two odd numbers, I assume with n not equal to m, then you get an even number. So that's a nice general case. So just to what Jackie has said is that if your two numbers are 2n plus 1 minus 2m plus 1, you get I think you get this, which is even. Oh, no, we want to add them, don't we? Sorry. We want to add them and get an even number. Okay, so I think we can place those two. So Liz, you're going to have to stop me if I get them the wrong way around. So I think they go that way around. Okay, now we sort of get to the slightly tricky parts because we've only got 6 left, but these are the hardest 6. We won't go through all the rest of these now, but by the time we got to this stage, you haven't got many options left. These two have to go together, which is quite nice. And then these four have to go together. But I will say that the thing that throws me, and I think, Liz, you said this through you as well, is that n and m are positive integers. And, you know, so far, we haven't had to use the fact that they're positive. And that comes into play with this one. Oh, somebody suggested some. Now, let's see if we can just finish this off. So n minus 2 implies that n is greater than 1. We've also had a suggestion of this one. Okay, we've had a suggestion of that. So let's see if that works. Oh. So this is one of those cases where we've ended up with 7 out of 8 correct. That means that perhaps 2 of these are correct, but they could be an if and only if instead. And if I remember correctly, I think it involves these two. This might be the right way around, it might not be. There we go. But do have a play with those. Yay, we've done it.
And Claire, I think I'm right in saying that, I mean, the interactivity is really useful. Some students, and if you've got the time and the resources, sometimes having paper copies of these to move around before you use the interactivity could be useful. And I think those are, there we go. Yeah. You can print them out there. Yeah.
So you can print out the statements here and arrange them yourself. Again, I would do it in very much a similar way to how we've done it. I'd have the 4 implies in one place and the 4 if and only ifs in one place.
So that's a nice way to structure your thinking, I think, there, isn't it? Yeah, lovely.
So that question there, this also introduces the idea of if and only if. And we have several other questions which use the same ideas. So I've already spoken about Iffy Triangles, where we've got 2 statements about triangles. Actually, the first statement, the one about the angles being in arithmetic progression, it is really quite a cute result, which you can prove going both ways. But obviously, you do need to know what an arithmetic progression is in order to complete that proof. We have 2 more problems which involve ifs and only ifs. The first one, which is called if, or if and only if, is about triangular numbers. And this problem has got some proof sources attached as well. So the idea behind this problem, we've got a couple of minutes. So think about a triangular number. So the triangular numbers are listed here, 1, 1, 3, 6, 10. We're going to take a triangular number, multiply it by 8 and add 1. So if I take 1, multiply it by 8 and add 1, I get 9. 3 multiplied by 8 is 24, add 1 is 25. Somebody's ahead of me already. We're going to get the square numbers. We're actually also going to get odd square numbers. So the question is, if I take a triangular number, multiply it by 8 and add 1, do I always get a square number? And then also, for every odd square number, can I write that as a triangular number multiplied by 8 added 1? So the idea of this process can happen in both ways. And if I just scroll down a bit, we've got, a couple of scrambled proofs for students to rearrange. And in the same way as before, we also have these as proof sorter cards for students to cut out and to move around. Okay, so that's if and only if. And the very last problem, I think I've got a few minutes left, is something called mind your P's and Q's. Now, we've labeled this as 16 to 18 because it does have some integration questions in it, but you can actually use it with Key Stage 4 as well. And I'll show you how. So this has got It's a bit like if and only if, but slightly more mathematical. So we've got 16 propositions, and in a very similar way to if and only if, you need to try and rearrange them. So you've got 4 of them which are if and only ifs, and 4 of them which are just in one direction. However, if you want to use this idea with key stage 4, if you go to getting started, then we actually have just 8 of the statements, and these are all the statements that do not include integration or trigonometry using radians. So these 8 statements can be rearranged to get 2 statements which are if and only ifs, and 2 statements which only work in one direction. And there's no restriction here. X could be negative, X could be, well, X has to be real, but it could be a non-integer, it could be negative. So that's something which you could use as a follow-up if you want. Okay, Liz, was there anything else that I needed to say that I've forgotten?
I don't think so particularly. Is it worth just mentioning that some of your tasks are live tasks?
Oh, yeah.
Claire?
Yes, so lots of our tasks are live tasks. That means that your students can send us in their answers. And what we'll do is we'll have a look through them and select some of the different approaches that students come up with, and we'll share them on our student solutions pages. We haven't talked about maxi pyramid, we haven't talked about sliding rectangles. These are all more problems which are sort of slightly logical in approach. So have a go at them and encourage your students to send us their answers, or their solutions rather than answers. We don't want an answer of 3. River crossing, if you haven't met it before, the first problem in river crossing is the one about the fox, hen and the corn, or you might have heard of it as being the wolf, the cabbage and the, I think it's still a chicken, and how to move across a river. But there's actually a slightly more, possibly slightly more interesting example, which involves adults and children. And that can be extended to be any number of adults. So there's a classic problem and there's a slight extension, which your students might like to have a look at. So I'm going to stop talking there and Liz is going to take back from me.
Thank you, Claire. Brilliant. I'm just going to share the final PowerPoint slide just to round up the session. Just to remind you that you can follow us on Twitter, and if you'd like to tweet about today's session, then do use that hashtag to join and encourage a conversation. That would be wonderful. Oh, look, my slide's gone all funny. I'm sorry it's gone black. Anyway, we can still read the link. An alternative way to keep up to date with what we're up to here at NRICH is to sign up for our email newsletter. But we send out messages roughly once a half term, so do that. We haven't mentioned more generally in this session our curriculum mapping documents. So you can go to that link there, the secondary curriculum page, and find links through to everything curricular focused on NRICH, including our mapping document, which links objectives from the secondary curriculum to NRICH tasks. So do take a look at that if you don't already know about it. Today, we've focused particularly on our latest feature about reasoning, but through that link, you can find all our previous ones. And I did post a link to one as we were going through that might be useful. It was the last few features have focused on proof. And so if that's something that you would find useful, do take a look back at those. Claire coordinates the STEP program here at NRICH. So Claire offers support along with other colleagues here for those students who are taking the STEP exam, so as part of Cambridge entrance, and you can find all the resources on that link.
And I'll also just chip in there for a second and just say it's not just preparation for Cambridge maths. The STEP support program has stuff which could be used to prepare for maths at any university. So it is particularly geared towards STEP exams, but it will still be useful even if your students aren't going to sit the SEP exams in year 13.
Thank you, Claire. That's really useful to know. We will put up the recording of this session on that link, so do feel free to share that with your colleagues or watch it again should you wish. It will be up hopefully by the end of tomorrow, this one, but at the very latest early next week. That is the link which I think Ems has also posted in the chat. We would love to have your feedback, please, about this session. As I said, we're funded by Trinity, and it's important that we do as good a job we can. So please do give us your feedback. Finally, you can, if you wish, sign up for the last secondary teachers event of this academic year, which will take place in June. Did I write down the date? I think it's going to be the 14th of June, Tuesday, the 14th of June. We look forward to seeing you there, possibly. Thank you very much for your participation. It makes our lives a lot easier when you readily contribute to the chat. We hope you find the tasks that we've introduced you to useful, and we look forward to seeing you again at another event. Thank you very much indeed. Goodbye.